Papa Flammy's Advent Calendar.
Here. Good morning, fellow mathematicians. Welcome back to the episode on Papa Flammy's Advent Calendar. And today, an absolute banger of an episode. At least I do believe so. It's the third video in my series on my school life, my exam life at school. And you know what? On Friday, I have wrote with my students the first time ever a calculus exam. It's the first time ever at my school for the past 6 years or something that we are having an Abitur class. So the highest education that you can basically get when you are still a student below the age of 18 or 20, you could say. So this is very exciting for me too. It's the first time I ever got to design an exam. And the one that I wrote with my students is around 7 pages long. They have 120 minutes to solve it. But what I'm going to show you today is the first draft of my exam. It's a completely different type of beast. And you're going to notice that, especially if you're from America, that this is probably not how you do calculus over in America. Because in Germany, we're going to go a different route. We are not going to go the shitty Indian way of just straight up calculating stuff. No, we try to make students understand and try to let them learn how geometrically you can interpret the graph of the derivative function and basically bring some properties of the original functions back. And you're going to see, I don't want to make this too long, this introduction, because I want to get to the main meat of the video very quickly. But before we actually dive in, don't forget to make use of the code to get 15% of everything over on my Spring Shop and also 10% over on stemwith.com on just everything. Support the channel this way and the Advent Calendar. Now, a few little details before we start. What I did with the students up until this point were limits, calculation of limits, what is continuity, and then we went to derivatives and calculating things like extrema of functions, inflection points, and the like. This is where we are at the moment. And last year we were talking about all types of functions that you can think of, exponential functions and their properties, polynomials, and so on. And it's gonna this exam revolves around derivatives and their applications. So how do derivatives apply to the functions? And the exam I'm going to show you today only has 5 pages. And the first 3 pages are a part where no calculators and lookup tables and the like are allowed. Meaning it's a no supports material allowed part. They got 20 minutes for it and you just make crosses and one explainer exercise. Then they are going to give it over to myself, and then here is where the real bit starts. And that's a completely different type of beast, as mentioned before. And you are probably, if you're an American, not used to this kind of questions over there. At least I think it's not how calculus is being taught at most schools over in America. But Germany is getting closer over the years to the American education standard, if you can even call it that, aka bullshit. We were once a country full of educational pride, and now we are a country full of shit. So we are getting closer to insanity over here, but at least I can do my part to make things better for my students and to really teach them logic thinking and prepare them for their studies at university later in the game. For the second part, they got 100 more minutes, so more than 1.5 hours to solve this right here. And it only consists of 2 exercises that might not seem like much, but it's a hard feat for the students to interpret functions for more than 1.5 hours at a time. And it's their first calculus exam ever, so it's also something completely new for them. So yeah, I'm really excited about those 2 exams that I have put out. You can find the download link to the German and the English version of the exam that I'm going to present to you today down there in the description, ResearchGate. The link is there. And also the link to my sadly only German exam that I seriously wrote on Friday. As mentioned before, it's once again a completely different beast to this one that we got right here. And it has its own nifty little secrets attached to it and things you really need to pay attention to. So you can download those and show it to your calculus teacher at school or something of that sort and ask them if this is a cool exam, because I for myself think that I am a person, I always design my own questions at all times. I never take questions from any other sources in a normal case. So 69% in reverse, so 96% of the time I do my own questions. And I always think that they are extremely well thought out and there is such a huge amount of structure in those exams. And you can let me know down there in the comments below if you think that this right here is a well-designed exam from your standpoint. And now we are going to go over to the chalkboard and now we are going to solve this one and you can try to solve those exercises with me too. Let's go. Alrighty, we are going to go about all the questions here chronologically. If there are any graphs where I need to explain anything, I'm going to draw them out very quick on the chalkboard and yeah, then we can simply continue with the next question after we have solved this one. So let us begin with how many real zeros does the function f of x is equal to x times x minus 7 times x squared plus 4 have. Now this right here is a function which is already kinda divided into its linear factors. It's a polynomial of degree 4 overall, so it can have at most 4 zeros, real zeros. One of the real zeros is 0 because of x, then x minus 7. If we add 7 on both sides, then we get x being equal to 7, and we got x squared plus 4. If we were to solve x squared plus 4, for its zeros, we are going to subtract 4 on both sides, and then we are going to run into a little problem. Namely, in the real numbers, this function is defined in the real numbers. This doesn't have any solution. So the answer here would be 2. We got 2 real zeros to this function. Now next up, the following graph shows the first derivative f prime of a function f on a certain interval given. The zero of f prime is denoted by x naught. Which of the following statements holds for f on the certain interval? Now let's take a look at the graph and it's fairly easy to interpret. Don't forget this right here is the graph of f prime. Goes like this and we got x naught here as the 0. Now the graph of the derivative of a function always shows us how the slope on the original curve behaves on each and every spot of x. Now let us take a look at the options that we have. F is strictly decreasing. Now this is not the case here because if it were strictly decreasing then all the y values of this function f prime would be negative. Same thing by f is strictly increasing, then all the y values, because it gives us the slope, so the y value corresponds to the slope of the original function, would be positive. Now what about f is strictly increasing for all x less than x naught? There would be that part here, and the question is asking for increasing. As mentioned before by the same arguments, on this interval here, it's decreasing because the y values of f prime are negative here. Now f is strictly decreasing for all x less than x naught. Now here we are getting somewhere because this is exactly what I said before. Y values are negative for this interval from x to x naught, meaning we are going to have the decrease of the original function. And f does not have an extremum is obviously wrong because the extremum of the original function f is exactly where we got a 0 of our derivative, because on an extremum we are going to have the tangent line, the slope is equal to 0. So this x naught right here actually corresponds to an extremum. So option D is the key here. I just love the D. For which of the following functions f holds that the limit as x goes to infinity of the function is equal to -1? Now we got several options here and we can just go through all of those one by one. Here's the main procedure that you would go through. This is just like testing for the asymptotic behavior of the function. So if we take the limit as x approaches infinity, I'm going to denote it with capital L, of x plus 1 divided by x minus 1. What we usually do here, what you learn in calculus class, is you factor out on both the numerator and denominator the x with the highest power. That would be just x, in both cases giving us the limit as x approaches infinity of 1 plus 1 over x divided by 1 minus 1 over x. And both numerator and denominator we factored out an x. It's going to be cancelled out, and now we can make use of the limit rules. We can track the limit to each the numerator and denominator separately, and then in the limit 1 over x for x to infinity goes to 0. This also goes to 0, so the first one would yield 1. So this is not the case. Now what about the other one? So we got 1 plus x divided by 1 minus x this time around. Now factoring out the x once again leaves us with the limit as x approaches infinity of 1 divided by x plus 1 divided by 1 divided by x minus 1. And now you can see where this is going. That and that is going to go to 0 overall, giving us 1 divided by negative 1 in the process, so the limit indeed goes to negative 1. And hence we are done. Just go through the options one by one, and that's it. Yeah, that is already done. And now, shown is the graph of the first derivative f prime of a polynomial function f. Polynomial means something of the sort, for example, x squared plus x plus c, for example. Which of the following statements is true for f on the following interval? Now, let us go through each and every option once again. F is decreasing for x between 1 and 2. Now, if we take a look at the graph, I'm going to draw it out real quick. Let us take a look at the interval from 1 to 2. That would be right here. Now, it says that f is decreasing in this interval. This is obviously not the case because, don't forget, this right here is f prime. That's the graph of the derivative function. All the y values here are positive, meaning the original graph is indeed increasing and not decreasing. F has two extrema. For the original function to have two extrema, what we need are two zeros of the derivative function. Now, we got two zeros here indeed, one at negative 1 and one at 2, but we also need to have, next to this necessary condition, a sufficient condition, namely that the second derivative is not equal to 0 of the original function. Now, we don't have this with this extremum here because now we have a double 0. This right here is a 0 with algebraic multiplicity of 2. And this suggests that our original function f has a saddle point because, you see, if we now take a look at the slope of this function f prime, which is the same as taking a look at the y values of f double prime, we are going to get that we have a slope at 0 here. Now for this point exactly here, we have that f prime is equal to 0 and f double prime, showing us the slope of the function f prime at each and every spot, is also equal to 0, which is not the right condition for an extremum. It's a saddle. So it doesn't work out. F has two inflection points. Inflection points are where the concavity of the original function is going to change. Now, the change in concavity is always given by the second derivative being equal to 0. This is like saying we are taking a look at f prime and we are going to differentiate it. And if you want to find the zeros of the derivative of a function, in our case f prime, what we are looking for are in fact the extrema of our function. F prime has two extrema, suggesting that our original function has two inflection points, which is the case, and then we are done. And the last one is f is a quadratic function. This is obviously not the case because the derivative of f prime would be a parabola, a quadratic function, because this right here is a polynomial of degree 3, and if we differentiate it with respect to x, we are going to get a polynomial of degree 2 out. So this doesn't work out. And then we are almost done. The first derivative f prime of x is equal to negative 6 divided by x to the third power, can be expressed as blah blah blah. Let us just write it out and see what we are going to get once we differentiate it. Now, we got our function f of x, and I'm going to rewrite it a bit. This is negative 6 times x to the negative third power. And differentiating this one is fairly easy. We are going to get f prime is equal to, this is basically just making use of the power rule. We are going to drag the negative 3 to the front, negative and negative positive 18 times x to the negative 4, which is the same as 1 over x to the fourth power, which is the last option. And now we are done with that, and we are almost done with the part where you can't use any lookup tables and calculators. Now the following image shows the graph of a third-degree polynomial f. Point W, W for Wendepunkt, inflection point, represents the inflection point of f. Sketch the graph of f prime of f into the above coordinate system on the shown interval. Let me just write it out real quick. And now we are going to go by the same arguments that we were employing when we talked about this graph. Now, we want to find the derivative function. So this time we are going to see how the zeros, for example, of the derivative function are going to behave when we take a look at the extrema, for example. Once again, the slope at an extremum is equal to 0. So the extreme points, the critical points here, correspond to zeros of our derivative function. So here would be a 0 and then here would be a 0. There are only two more things that we need to take a look at. This right here is a third-degree polynomial, meaning the thing that we get when differentiating is going to be a parabola. As mentioned before, our inflection point always corresponds on our derivative for an extremum in some kind of way. So if we draw the line right here, that would be like the line for the critical point of our inflection point. Somewhere on this line we get an extremum, but we don't know if it's a minimum or maximum yet. This we can decide by taking a look at the slope of our original function. Up until this extremum, this first one right here, this maximum, we have an increasing function. If we have an increasing function, that means the derivative is always going to be in the positive y values at first. This is what we are going to get. Meaning, our graph would probably look something like this. Something of that sort. It's a parabola which is going to be decreasing in the derivative at first, and then we are going to get a high spot once again. And on this interval right here, you see this, we are going to get a decreasing function once again. So on this interval, we also need negative y values up until we reach this point once again, and then it's going to be negative still, and then increasing overall, so positive y values. And that's almost it. The last thing, explain why the following statement is true. The graph of the second derivative f double prime of f is a straight line. What does it mean for a function to be a straight line? It's just overall a linear function. Now this is very easy to show. Now if we take a look at f, it's gonna correspond to something x to the third power as the highest term. You could write it out. This is the same as ax cubed plus bx squared plus cx plus d. If we were to differentiate this, we are going to get that this thing right here is 3ax squared plus 2bx plus c. And if we differentiate this once again, we are going to get finally that this is going to be 6 times a times x plus 2 times b, which is the same as saying we have mx plus n, which is a linear function because the highest exponent is 1. And this was the part without calculator. I'm going to erase everything from the chalkboard. And I hope everything I said was clear up until this point. And then we are going to get to the fun part. We are going to continue. Now what we have given in the part where you can use calculators and lookup tables and the like is on the first exercise the graph gf prime of a function f prime, which is the derivative of our original function f. Now f prime is a third-degree polynomial, and the tangent at the inflection point w, because of Wendepunkt, this right here is w, and it has the coordinates 4 and 1. The tangent line has a slope of negative 0.75. I always tell my students that all the information that you have here is necessary in some kind of way for the exercises, but they always forget about this, and then, yeah, shit is burning down rather quickly. But those are the parts of information that we have given, all the snippets. And now, explain why the graph of f can have at most one extremum. Now, let us recall what we have talked about before. We have the derivative function given, and all the zeros of this derivative function are going to correspond to the extremum, so those are the critical points of our original function f. As mentioned before, we got the same situation. We got two zeros here, but one of those zeros is going to correspond to a saddle point, because here we have that f prime is equal to 0 and f double prime is equal to 0, which is not the sufficient condition for an extremum. And hence we are done, meaning only this one at 0 is going to correspond to an extremum. For the B1, this is just a little gimmick because you found out about the first part, so you can get yourself a little point here. Namely, name the values of all the critical points of f. Well, I shit you not, it's this one right here, x not being equal to 0. And hence we are done with this exercise. Explain why the extremum of f must be a minimum. This is rather easy to explain if you think about what we have discussed before. Namely, if we have a minimum for minimum on a function f, we always have a decrease of our original function up until this point right here, and then we get an increase of the function f. Now, a decreasing function, or monotonely decreasing part of a function, always corresponds to negative y values on the derivative function. We are going to go in from the negative y values, and then we are going to go into the positives. This is exactly the condition for, well, a minimum. And yeah, this is what students need to write out in a nice little sentence. And that's already it once again. The graph of f prime has two critical points. Explain the importance of these points for the graph of f. Listen to the exercise. The graph of f prime has two critical points. Now, what are the critical points of our function f prime? They are those ones here. They are the parts, or the x values, of our extrema of the derivative function. Listen to what I said before. The extrema of the derivative function always suggests that we have inflection points on the original function. This is just what we did with the graph before, where we have drawn out the derivative graph of the original graph. And yeah, that is the answer. Those critical points correspond to the inflection points. And yeah, we are almost done. You might think that this is easy, maybe because you have done mathematics for a bunch of years, but this shit is extremely hard for students. It's not calculating what you do here. You need to really think geometrically. And this is the real difficulty with the German Abitur. Draw the graph of the second derivative f double prime of f into the above coordinate system. Okay, let us do this. Let me get my my SpongeBob here, my SpongeBob. And now, f double prime is the derivative of this thing. And now we are going to go by the same means as before. It's not much that we need to consider. At first, we have this inflection point on this function here at 4 and 1. Now, somewhere on this line, we get the critical point for our derivative of the derivative, f double prime. So somewhere here is going to be a minimum or maximum for f double prime. Now, the extrema that we got right here are going to correspond to the zeros of the derivative of the derivative. So somewhere here, it's going to pass through. And now the last thing we need to think about is going to be a parabola once again. Do we have a minimum or do we have a maximum? Once again, think about it. Our function is at first increasing, meaning for f double prime, it's going to come out on the positive y values at first until it's going to change its monotonicity, I think it's in English, at this extremum here, and then it's going to go up. But you need to be careful here because we have one more thing given in our original text of the exercise, namely the slope of the tangent at the inflection point is negative 0.75. What does that mean exactly? The slope is always going to be given by the derivative of our function, meaning f double prime is going to be negative 0.75 at our inflection point of f prime. And this is what you really need to consider. Here, I'm not going to allow any kind of sketch. It needs to be accurate, meaning at negative 0.75, we are going to get our minimum here. And this is what it's going to look like. Read the exercises. I'm thinking all this shit through to the very last piece, to the very last nut and cranny. So you really be careful, bitch. Sorry, the camera stopped. The recording is going on for quite a while. Now, calculate the slope of the tangent t and its normal n of the graph of f at x, w being equal to 2. Now, xw is the critical point at x being equal to 2 of our function f prime, but this is always going to correspond also to the critical point of the inflection point, one of the two inflection points on the original function. Now, is there even something to calculate here for the tangent t? Think about this. We want to find out the slope of the tangent of the original function. The slope of the tangent is going to be the same slope as the function at that point, x being equal to 2. Now, what is the slope of the function at x being equal to 2? Well, this is just the y value of f prime at this critical point. Namely, the slope of the tangent f, it's gonna be 2, m being equal to 2. Now, if you want to find the slope of the normal, well, this is just gonna be the negative reciprocal of that. So we are going to get the slope of the normal is negative 1/2, and then we are already done. It's not about calculating here, it's about thinking logically. Critical thinking is what's required in Papa Flemmy's class. Explain why using gf prime, okay, so we need to use the graph that we got here, why the graph of f is increasing for all x greater than 0. That's very easy to explain because all the y values here are greater or equal to 0. It's not strictly increasing on this interval because we have a 0 value right here, so we get a saddle point in some kind of way, meaning it's just monotonous. It's not decreasing or increasing here, but overall, the condition that we need to have is that all the y values here are gonna be strictly positive or 0 for the original function to be increasing on this interval. Draw a sketch of one possible graph of f. Now this is going to be a little bit of a mess, so I'm going to draw this out once again. And now we need to think backwards. I've drawn it out and now we need to think backwards. So in terms of integration or in terms of geometrically putting this back to the original function. Now once again, our zeros right here are going to correspond in some kind of way to the extrema of the original function. So here we are going to get an extrema in some kind of way, and here we are going to get a saddle point, as mentioned before. So everything that we have concluded up until this point will be used in the last part right here, in this little bonus one, this little bonus chapter. Now number 4 right here, the x value 4 is going to correspond originally to nothing. No, forget that. See, I'm being confused here too, because it's really hard to think about stuff like this on a continuous basis. The extrema of our derivative function are going to correspond to our inflection point in some kind of way. The saddle right here is going to be an inflection point too. So somewhere here we are also going to have an inflection point on this line. And now the last thing we need to think about is how is our function increasing or decreasing on this interval? And then we are basically settled, you could say. Settled because of saddle. Oh my goodness, please kill myself. Now on this first interval, up until we reach this extremum of the function, we are going to be decreasing. So it's gonna come down from here, ending us up in an extremum, a minimum at that. Now next up, it's gonna be increasing up until we reach our inflection point here. When we reach the inflection point, we are going to change the concavity. So we are going to go from a convex function or convex part of the function to a concave part of the function, meaning it's going to go like this. And then we are going to reach in some kind of way a saddle here, and then when this saddle stops, it's going to be strictly increasing once again. So it's going to look like this. So our function in theory should look like this one right here. In some kind of way, but this is just obviously one possible function because you can just put a y-intercept here plus c integration, but the students don't know about this yet, and you can just put it upwards or downwards on the graph. Very cool, right? And now for the last exercise. We have the normal on a straight line given. And the normal, the function here, is going to be na of x being equal to, that's the only part where you really need to calculate on this exam, is equal to negative 2x plus a, where a is element of the real numbers. And now we need to find the equation of the function g of x, which is a straight line. G of x is the line where our normal is set on, which passes through the points 0 and negative 2. Now let us do this. Remember what I said before, and I'm going to put this piece of paper here for now. If you want to find out the slope of the straight line, or vice versa the normal, we are going to take the slope here and we are going to take the negative reciprocal. Meaning g of x looks something like negative and negative is positive 1/2 x plus, c. We don't know what the y-intercept is yet, but for this we have a point given. Namely, if we plug in 0 and -2, at least I think that it was that, 0 and -2, what we are going to get is that g of 0 is equal to -2 is gonna be, that part right here is going to vanish, giving us a y-intercept of -2, meaning the function for our straight line is gonna be a -1/2 x, no, +1/2 x, -2, that way. Okay, so we got this right here and we got our normal. Now, the next part of the exercise is getting a bit messy over here, I'm terribly sorry. Draw the graphs of both functions g of x and n0 of x into one coordinate system. Now, what is n0 of x? N0 of x is going to be the same as -2x. And that is very easy to draw into a coordinate system. So meaning, if we draw this out, we are going to get -2x. It's going to be a parent function. It's going to pass right through the coordinate system's origin, and -2, so it's a decreasing function overall. We are going to go 2 steps downward and 1 step to the right, giving us this function right here. And exactly at, no, we don't have a point given where they both meet. This is why you need to draw those out. That's a part of the exercise to see it visually. We can just plug values into here and see where everything passes through. We know that g of x passes through -2 here. And in normal case, you can just make use of your geodreieck, so this little right triangle thing that you use in school, this ruler type of thing, and just put it on here and see where you are going to get a right angle. And then you can call it quits, but you can also plug in another value basically for x and see where it lands you. If we plug in 2, then we are going to get 0 out. That's actually kind of convenient. No, you are going to get -1 out. If we plug in 2, you are going to get -1 out, meaning it passes through here, and then you can just draw this one out and you get something that looks like this. And then we are done. Nice. Okay, next up. Let PA be defined as g times NA, as the product of those two functions that we have given here. So PA of x is the same as those multiplied together. Namely, we are going to get -2x plus a times 1/2 x minus 2. And the first exercise is to calculate the equation of the function PA of x. Hey, we are done. That is very nice. Calculate the real zeros of PA. Now that is very easy to do. It's already deconstructed into linear factors. So this function can only be equal to 0 if this part is equal to 0 or if this part is equal to 0. So let us solve it, shall we? So we get -2x plus a is equal to 0. It's going to result in subtracting a on both sides and dividing by -2. It's going to give us x1. In this case, you get 2 real zeros, obviously. x1 is going to be equal to a over 2. And what about x2? Now, if we were to solve this for 0, we are going to add 2 on both sides, multiply by 2, we are going to get that x2 is equal to 4. And hence we are done. Those are the real zeros of this function. And this function is going to be a parabola overall in some kind of way. And that's very cool that one of the zeros is always going to stay at 4 and the other 0 is dependent on our parameter a. That's a so-called Funktionsschar, and this is what we like to have on our Abitur exams over here in Germany. I'm going to erase everything real quick and then to the last 3 exercises. Draw the graph of the function P0. Let us write out what P0 actually is. P0 of x is the same as if we plug 0 into here, we are going to get -2x times 1/2 x minus 2. And now we need to draw this function. It's gonna be a parabola. The only thing that we really need for parabola to draw are 3 points overall. We always have zeros given, so we know that the x1 is equal to 4. We know that x2, at least this is what I would do, is going to be equal to a over 2, but a in our case is 0, so it passes through 0. And now we just need to find a less point, and then we are basically done. If we plug 1 to here, for example, no, let us go with 2 once again, then we are going to get -1 here. So 2, we're going to go with -1 here. -1 times -4 is going to be 4. 2 and 4 is going to be 1 point where it passes through. And then you can basically draw this function. You can also take a table of values and just pump out more stuff. Or you could calculate, for example, the high or low point of the function, the maximum or minimum, whatever it is. It's going to be a maximum because it has a negative slope here on the leading part of the polynomial. No matter what you do, it's going to look like this in some kind of way. Passes through 0 and 4. And then we are going to get on 2, 4 up here. And I think by coincidence, this is already the maximum value because it's right in the symmetric center of the pitch. So I think we are on to a winner here. Yeah, this is what the function should look like. At least I think it does. I haven't calculated through this exam myself yet, so I only thought about the questions, but they are pretty good. I like them. I always like my own exam questions. Now show that the extremum of the graph of PA is always a maximum for all A element of the real numbers. Now there are several ways you could show this. You could say that the leading coefficient of x squared is negative, so it's opened in the downwards y direction, giving you a maximum. But we can also go the differential calculus kind of when I'm going to do this, and we are going to differentiate this bitch boy right here. Gonna calculate PA prime, and then we are going to find out for which value of A we are going to get a maximum probably, and if it's always a maximum. Now if we differentiate this, we can make use of the product rule, for example, or we could just write everything out and see what we get. This thing right here is, if we multiply it out, just negative x squared, and then we are going to get plus a over 2x plus 4x and then negative 2a, which is the same as this one right here if we factor out the x on this term. Now we can start differentiating this one, and then we are pretty good to go. We're going to get negative 2x. This right here is going to vanish in the process, the y-intercept, and then we are going to get plus a over 2 plus 4. And now we can solve this right here. Okay, in the normal case, we only need to show that it's always a maximum. So what you would do, this right here is the necessary condition. You would go for the sufficient condition. PA prime of x is going to give us negative 2, and this is less than 0, giving us a maximum overall. So this already concludes the exercise. But if you want to find out what the a value is, for which you get the maximum, or where the a value of the maximum always is, or the x value in terms of a, we can solve this one right here. Let us do this real quick. I think you could use this for the last exercise. Calculate the one value of a for which the maximum of the graph PA will lie exactly on the y-axis. Yeah, so it plays into there basically. So we can solve this part right here. We are going to get that a over 2 plus 4 is the same as 2x. Dividing both sides by 2 is going to give us that a over 4 plus 2 is equal to x. And the last exercise asks, when is our maximum right here? Somewhere on the y-axis, exactly on the y-axis. And this always happens when x is equal to 0. So when is this equation right here equal to 0? This is what we are looking at. This right here corresponds to f prime of 0. Well, we can solve for a now. We can say we are going to get negative 2 here, and then by 4 we are going to get a being equal to negative 8. And we know that this is always a maximum. So for a being equal to negative 8, our parabola will lie on the y-axis, exactly. And that's it. There's not much more to do. Maybe you guys found it difficult, maybe you didn't, maybe you are so well versed in mathematics that you thought this right here is child's play. But believe me, if you're doing this for the first time and you were at that point in some kind of way, this shit is pretty hard and you need a lot of imagination and a lot of creativity to solve those exercises. And as mentioned before, I'm not one to brag about stuff, but I think that this is a very, very well designed exam. You could say that it's not. Leave some comments down there below. I want to hear your feedback. As mentioned before, I also have the other exam that I actually wrote in my class on Friday, uploaded on ResearchGate 2. It's completely in German, but maybe you can put it into Google Translate and see what you get. It's a different type of exam. It employs some of the same strategies and the like, but with a bit more calculation and stuff. So it's a bit more student-friendly, you could say, I suppose. So yeah, you can also check this out. Take a look at all the links down in the description. I hope you did enjoy what you've seen today. That was a longer video, but it was a lot of fun to solve the stuff right here. And more to come. I plan on showing you most of my exams over time here on this channel. And I hope you want more. And if you do, please leave some comments down there below for feedback. Don't forget to check out my Spring Shop and also Stemmish.com to profit from the nice discount code and to support the advent calendar. I'm putting a lot of effort into this beer. And up until next video, I wish you guys a flammable day. See ya!